Okay, so the handout I've given you is from this book by Carol. Space, Time, and Geometry. It's excellent. It's very good. If you look on the web page where the lecture notes for this, I think before you actually went into an actual book. This is actually one book. Books are expensive. This is might be one at some point that you might want to actually consider on your shelf. It's worthy to be on somebody's shelf. It's an excellent book. Um, some of the derivations that we've used in class have actually come from this. I photocopied this section here. I think he has one of the better arguments for it. There's pages upside down. Sorry about that. I think everything else is right set up. And so we're going to follow more or less the details. We're going to follow this. There's going to be a couple of daily homework assignments that are going to come from this, where I'm just going to state the result. For daily homework and for homework, you're going to work out some of the results. So what I want to do is, before we get to that, let's go and let's ask, how long would it take you to actually drive to the center of a black hole? So in other words, you're hopping in your spaceship, you're going straight through the black hole, you're looking at your watch, and how long would it take you to reach oblivion? So that's the question we can ask. So how long would it take uh take to reach the center of a black hole? Okay. Starting at rest from some initial point are not, according to the wristwatch, time of the observer. So in other words, this is you. So you're going to be at the spaceship, you're going to be flying there, you're going to be looking at your watch. How long would you take it? Says how long would it take you to reach the center here? So this is really going to be the proper time. So the wristwatch time here, this really is this part here. That is really the proper time. That. Okay, so let's start off. We're going to start off with our metric. I'm going to put the C in this piece here like that. Here, plus dr squared, 1 minus RS. And when we do this, this is going to be radial motion. So I'll have to plus 0 here because we're assuming theta and phi are fixed. This is going to be radial motion. So what do we do here? Well, I'm going to divide through by the d tau like we've done before. D tau squared. And what did we say that this side here goes to? For matter. Oh, that's minus c squared. And again, if it's for light, it actually be 0. For matters, that should be minus c. So this is this minus c squared equals 1 minus rs over r. dct over d tau. Oh, that should be, I did my dct, I did not square it. That was a y. So that's what we had. Now the trick for this is we're going to use our conserved quantity from the killing vector to get that here. So we're going to use our conserved quantity here. So use the killing vector for this. So we're going to use the killing vector to get rid of that. And let's just go through that argument again. Okay, so what does that give us? So remember what we have here, the killing vector states that this u mu k mu equals a constant. That's what we had here. And for the timepiece, we know that our k mu is this guy. And so that really is this u0. And u0 we said is a g00 times u0. That's what that is. So maybe I can relate this. One in here. That. And then the g00 is this minus 1 over 1 minus rs over r. Because that's our g00 right here. And then this in here is this dct d tau. And this has the equal constant. Oh, there's a mass in here too. For no, I'm just going to look that. So if we put the mass in here, I'm going to multiply everything through by minus MC. M is my reference here. And if I do that, I get the following. I get this M. Let's see. One minus, oh, y'all me here? This G00? Oh, yeah, it's this. I was thinking, wow, I'm getting a weird term here. That would untrue. Sorry about that. So this gives us M C squared here. So I've put a minus sign here. Here's my M. I've taken that C, but with this C, I have this 1 minus RS R dt d tau equals a constant. So let's assume that we're far away and we're at rest. So if we are far away, if we are initially far away, far away and at rest, this quantity here goes well. This R is large here, so that goes to 0, and from at rest, this just goes to mc squared. And so our constant here I'll do it this way. This gives me the mc squared, 1 minus 0. This just gives me dt. We're at rest, so they do the same thing here. This is my constant. So my constant is this mc squared. That's my constant. And this is just your total energy here. I'll just call this E. That's your total energy. So this constant here, by multiplying through by this minus, is just my total energy. So the sum is squared. d tau is just by energy or E, which is this mc squared, doesn't change. If I divide through by this mc squared, this tells me and I get 1. So this tells me dt d tau is this. Okay, let's stop at that. Does that make sense? Okay. So we're going to take that and put it back into our metric. So if we go back into our metric, this piece now becomes 1 over 1 minus rs over r squared, right? Because this is my, oh, there's a minus sign here still. This term here is my dt d tau. And this is one of the factors down here. So if I multiply by 1 minus rs over r, okay, what happens here? It gives me the following. That would give me minus c squared 1 minus rs over r equals 1. There should be a c squared here too. So this is my minus c squared here. dr d tau. Makes sense. I multiply this through. They go out, and this gives me c squared r squared equals r dr d tau on c squared. All right. If I take the square root of all this, and that's a set tau. Now, I actually do have to look at the negative root here. Now, why would I have to look at the negative, right? If you take the square root, it's a plus or minus root. And why would I need the minus sign here? Think of what we're doing. We're falling into a black hole. This side is positive. What do you know about the drdt or drd tau? You're falling into the black hole.
It's negative.
It's a negative. So you have to put a minus sign there to make sure that both sides are positive. If you're going away in the other direction, then it's going to be positive. So you have this here, and so now we can integrate this. Okay, so if we do this, they come to tau, then integrate it from some 0 to tau time. Then integrate this from some value R naught, here's my minus sign to let's say R. And this is my R to the 1/2 dr. So this is basically when I start my wristwatch. I start my wristwatch at this time here. So this gives me C square root of RC, or sub S, tau, equals minus, and this gives me 2/3 R to the 3/2, evaluated at R naught and R. If I take things over here, this gives me R to the 3/2 minus R naught to the 3/2. But put this over here, then take the 2/3 root. Actually, no, like that.
You meet your tau too.
Drop it from here, thank you. Now, if we're at the center of the black hole, your little r is 0. So you can see this term goes out, the minus signs cancel. This gives me 3/2 C square root of R sub S equals R naught to the 3. So your R naught, you're with a tau. So if I solve for the time, it's going to be 2/3 R naught 3/2 C square root of R sub S. Okay. The main thing is that this is a finite time. And also, when we did that, nothing weird happened going through the event horizon. From our point of view, we just went through the event horizon, and in this amount of time, we reach a goal again. When we look at the tidal forces, we're going to be shredded at that point. But we at least our shreds would reach this energy. That makes sense? Now, the problem, as we mentioned before, is what would then your parents see? And your parents are not going to see you reach to the center here. This is what you're going to experience because you're looking at your own a watch. And so this would actually be the proper time according to the actual observer. Now, somebody watching from the outside doesn't see that. Now, I'm not going to put in all the details because you're going to work in all the details because it turns out, okay, the integral will look kind of messy. It's not this thing. Now, what would an observer, let's say, what would a stationary do? See. Okay, now we've looked at this before, but let's do it again. So here's our RS. And here's our R. And when we looked at our metric again, I'll put that C with the T again. What did we say our observer sees? So for light, what would then the DS be? 2. So for light, what does this hole here hold? Zero. Okay. It's always zero. For light. And so we worked this out last time. Well, actually, at some point, I don't remember when. I had zero, so I could take this over here and this off the this ratio here. That gives us this. This is all we get this. And we said, if you're really, really far away, the drop here, that looks like this. Right? Because if you're far away, the R is large, so this is R large. And so what happens here is that this ratio here looks like plus or minus 1. So it just looks like your normal light cone. We said as R gets closer and closer to R sub S, what happens? Well, this bottom here gets smaller and smaller and smaller, so the whole thing gets larger, larger, larger. So that starts shortening up. As you get closer, this goes like this, and it goes like this, and when you get really, really close, it's like that, and then here at that point, it's like this. So what would happen here if you're moving in here and then sending a signal? And he has a nice picture of that. So if you take that hand out and turn the page, he has this picture here. Okay, so first of all, I'll try to convince you of this in just a little bit. What I'll show you is that your parents are going to see this path like this. So this is the path of your ship that your parents are going to see. And let's say you're going out here and your parents are over here. So your parents are here, this is the world line for your parents. And you're going this way, and on regular intervals here. So this is regular intervals on your world line here, you're sending out messages. And if you look here, they actually have taken this equation that I just erased. We actually already integrated it the other day. And they plotted this out of the lines here with this, the dotted lines. So this is basically you sending out regular messages like this. And what's going to happen here is that they start going, there's an arc to them like this. So the closer you get, the spaces get bigger and bigger between these things. Then way up here. So this distance here, this distance is bigger and bigger. So this we call delta T. What does he call it? He just calls it delta T1, delta T1, delta T1. Then what's going to happen here is that this delta here, which he calls delta T2, is here. And then this one over here, this is delta T2 prime. It's just getting bigger and bigger and bigger. Then you get like delta T2 triple prime. Your parents, again, if you're sending a message, they're basically going to see the distances between your clock or whatever beacon you're sending out, which is like a laser pulse, getting larger and larger and larger. Now, what about this curve here? What would your parents say? How long would it take you to basically get to the center of the black hole? Well, what your parents are going to do, they're going to work out the details. Part of the details here. Your parents are never going to see you actually cross here. What they're going to see is that as you move closer and closer here, what they're going to see is that effectively you just basically hang here. You're never going to, they won't, from their point of view, they will never see you crossing the horizon. As far as they're concerned, you're basically at the event horizon and you're stuck and you can't get out. And so what I want to do is show you how that works. And then we have to figure out we understand what's going to happen with that, but we have to figure out how we can get better coordinates. And the whole process of getting better, of writing that metric in better coordinates that don't have this pathology here, that's going to give rise to basically a quest to basically figuring out exactly how you can take that metric and view every aspect of that metric, every single, basically, how can you take that metric, which is time symmetric, meaning that you can take t and replace with minus t. How can we look at some coordinate system will allow us to look at every aspect where that metric is valid? Not just up here, but inside here, in the past, and the present, what we're going to do with all that. So let's see what we can do with that. So, what is dr dt? That and that an observer at rest measure. So if somebody's at rest, they're going to measure dr dt. They're not going to measure dr d tau. Because again, remember that t is that far away time. Basically, if you're far away here, that'd be the time that you're doing. So this is what your parents would be. So your parents are measuring this. Unless I should figure out what that would be. So we go back to our metric. Well, actually, we're gonna do the following. We're gonna have math. Okay. What's the most important math techniques we have?
Separation of variables.
Separation of variables. Taylor expansion.
Add 0 in clover fraction.
Add 0 in clover fraction.
Multiply by 1.
Multiply by 1 in clover fraction. Which one are we going to do here?
Multiply by 1.
We're going to multiply by 1 in a clover fraction. We're done. Okay, our clover fraction is going to be, we're going to basically write this as, going to multiply the top and bottom by 1 over d tau. And what does that give me? That gives me dr d tau over then dt d tau. And we have one of these. Okay. We had this one from the previous result, and that gave us 1 over 1 minus rs over r. Okay, then what did we have for this one again? You're gonna have to flip it. I think, or maybe we solved it like that.
Oh, is it this thing?
Let's see. We're just gonna steal it. Yeah, so if you took the square root of it, you'd end up with this minus square root of rs. So this guy, that would be tau, is that still on the board? That is. Is going to be this minus square root of rs c all divided by r the 1/2 power. That's what we have there. So now if we put this over here, what does that give me? That gives me dr dt equals minus c square root of r sub s over r to the 1/2 power. And then this is 1 over 1 minus rs over r. So I can flip that up. And if I want to actually then solve this equation, I'm going to take all this to that side and dt to this side here. So this will give me r to the 1/2 power over 1 minus rs over r dr. So that's taking the 1/2 over here, dividing through by this factor. And that's equal to minus c square root of r sub s d tau dt. I'll clean this up a little bit here. And that gives me r to the 3 decimal. R minus r sub s equals minus c, oh, I'm up with a gr here. Minus c square root of r sub s dt like that. And then this we have to integrate then from some r naught to r, and then from some 0 to t. Now I'll do the right side for you. Okay. This is minus c square root of rs with minus sign here, t. There. Okay. This side here is a mess. Okay. That side ends up being, that's just an outright mess. And you're gonna have a whole bunch of terms in there, almost none of which I remember. However, you're gonna have the following. When you actually do this here, you're gonna have some stuff up here. And at the bottom, you're gonna have also some stuff up here. You're gonna have some other stuff here, plus some stuff. I have to work it out every single time, and you're going to get basically r minus r sub s here. Like that. Okay. And this is going to be related to your time. So here's the problem here, is that as your r gets closer and closer to r sub s, what happens to this argument here?
Goes to 0.
The bottom does, so the whole thing goes to infinity, so the time is infinite. So as far as they're concerned, you don't, as you get closer and closer to that event horizon, they're going to see that time actually gets larger and larger and larger, and eventually go to infinity. So as far as they're concerned, you never even cross that event. And the reason why is because that light cone narrows up like this, and eventually that light cone, you right here goes like this. So we'll say these light rays here are never, they're basically always gonna go like that. And so your parents will just be seeing these, you know, because your parents were like that. These messages as you get out, as you know, your path like that, the distance between those pulses just get larger and larger and larger and larger. Your parents are just gonna see them. That makes sense?
So
Even though you yourself have now gone through like boom, and you crashed into that. So you're dead, but your parents will never see you die. You're just instant this. So as far as they're concerned, you never even cross that boundary horizon. You know, they can just go and rescue you at some point, even though your mom's instead.
So will it just like will they just always
They'll just always see you just basically hung here. That's all they'll see. Even though you yourself went into oblivion.
how does like the way light like
Now, what's going to happen? I haven't looked at the wavelength yet. Okay. It's going to, what they notice is there's going to be basically your things are going to get basically become more red and red and red. There's going to be an infinite red shift. And so they would actually see the color change as well. So basically, any color from here, it's going to get shifted further and further and further to the right. And so they basically just see that have this infinite red shift. But they would only see that red shift basically at the event horizon.
But if you go like this and you go right in, isn't there
This is you, but when we do this, that's it. You're looking at your wristwatch.
Yeah.
Okay, they're not. They're measuring this time here.
Yeah.
That's what they're measuring. But
Yeah.
you are measuring the proper time.
But isn't there like a limited amount of photons that you actually like give off?
Well, and then because basically, I mean, it's there's no limit on the number of photons given off here, but what's going to happen is that any light that is emitted here is going to be shifted to the farther. In other words, you might have a wavelength like this, but that wavelength is going to start getting shifted more and more to the red. So as you get closer, it's going to start looking like this, and it's going to start looking like this, and then it's going to start looking like that. So the wavelength gets infinitely large.
I see.
The upshot of this is don't drive into a black hole. Okay, that's the important. Wow, life lessons, you know. Okay.
Yeah.
Now, as far as actually going from here to here, it's kind of a pain, which is why I'm giving it as a exercise. I'll break it up into steps for you to do this. Okay, but it's a good exercise to do. So the problem here is that we would really like coordinates where I can actually look inside here, because the coordinates we have here with that t, they're really good for here. But if you want to find out what's going on inside here, they're not, because basically because of this phenomenon here. And so it'd be really nice to switch to some form of coordinate, which would allow us to basically explore basically outside the black hole and inside of it. And we're going to find later on, since we have this d squared here, t and minus t are both solutions. So not just do we want to get basically outside and inside of black, we would also like to account for the fact that you could have t or minus t. So we'd like to look at every aspect of this metric here, every possible aspect of it, and that's going to give rise to the crucible. Okay, well, bit by bit. So the question is, how can we actually look at what's going on inside the black hole? And so what I like what Carroll does here, I think he's correct in this approach. He basically takes baby steps. He keeps on doing better and better coordinates, and eventually gets to the ones that are going to allow us to look at everything. So the question is, the R and T coordinates that we initially used in deriving the Schwarzschild metric are very good when R is greater than R sub s. But they don't work well when R is less than R sub s. And we saw what part of the problem is. The problem is that really that time coordinate is not behaving properly. So one of the problems is the t coordinate. Again, this is the time for somebody far away. Looking at this, it's just not working well. The t coordinate does not work well. Okay. So what we're going to do is, I think he calls it the tortoise coordinate. What was his name for it? Tortoise coordinate. So what we're going to do is we're going to switch. So recall. So we will switch coordinates to do something that will allow us to explore both inside and outside the black hole. Okay, so recall on Friday, we had and we just had it right now. We had this equation. We had that. We multiplied the top and bottom by r. And then we divided this into this. And that gave us this. We have that. Okay. And we integrated that. And that gave us the CT equals plus or minus R minus this RS element of R minus RS. Plus the constant. Here we have that. And I'm going to tinker with that a little bit here. I can rewrite this expression here. I can pull out an R. I can write this as this. Factor out an RS here. And I know if I have the logarithm of two things being multiplied, this is the same thing as log of RS plus the log of R RS minus 1. And this is a constant. So I can take that constant and combine it with another constant and just write it like this. Now he's going to call this coordinate here the torus coordinate. How on earth this called torus? Okay, so he's going to take this whole thing here. He's going to define this to be R star. And he calls this the torus coordinate. And what is this is sad. What he's going to do is that he's going to switch. So basically, he's going to rewrite the metric. Instead of writing it in terms of R, he's going to write it in terms of R star. So that's what we do next time. And there's a reason why he's going to do this. And go over it next time. And it's not going to be perfect, but it's going to give us an idea of what to do. It's going to start pointing things in the right direction. So next time, what we're going to do, we're going to, instead of having this guy here, or minus dt squared plus some stuff dr squared, we're basically going to rewrite this term here in terms of R star squared. And we're going to look at that. And that's going to help. There's going to be some improvement. Or, okay, it's not great. But it's going to give us an idea of what to do. So what I like about his approach there, instead of just writing the whole, let's do the following transformation, which is not one bit obvious. He builds it up by basically fixing problem after problem after problem until you can actually see where the actual final transformation is coming from. So he builds up the idea because we're going to have a really non-obvious transformation. But he's going to develop it in a systematic fashion. So what I'm gonna do is I'm gonna start on this point here tomorrow, and then we'll go from there. And also, are we having class on Thursday?
You so?
Okay, good. Okay. I'll mention it tomorrow. Okay, we're done.